Welcome. If you're cramming for an AI exam or, just finally trying to get your head around what a neural network actually is, you have come to the right place. We are about to break down the absolute fundamentals, everything you need to know without any of the fluff. Okay, so here's our game plan for today. First, we're going to tackle why we even need these things. Then, we'll get our hands dirty and dissect the anatomy of a network. After that, we'll see them in action with a couple of real-world examples. And I'll wrap it all up with a cheat sheet to make sure all these key concepts really stick. So, first up, why did we have to go and invent neural networks anyway? What was so wrong with the models we already had? Let's dig into the problem they were designed to solve. Let's start with a really basic question. We've all heard of models like linear regression or decision trees, right? They're kind of the workhorses of machine learning. But do they have a breaking point? And as you've probably guessed, the answer is a resounding yes. And this is really where we start to see the cracks appear in those classic models. Take k-nearest neighbors. It just gets completely bogged down and slow when you throw a ton of features at it. And models like logistic and linear regression, well, they're fundamentally limited. They can only see the world in straight lines. They all hit a wall when data gets messy, complicated, and nonlinear, which, let's be honest, is how it is in the real world. So here's the absolute core of the problem. A linear model can only draw a straight line to try and separate your data. But what if your data looks more like a spiral? A straight line is useless. The solution that neural networks bring to the table is the ability to draw curves. By using these things called hidden layers and nonlinear functions, the network can create a flexible, squiggly boundary that can actually wrap itself around the complex patterns in the data. It literally learns how to draw the perfect curve all on its own. Okay, so now that we know why we need them, let's peel back the layers, pun intended, and see what a neural network is actually made of. From a bird's eye view, a network is pretty simple. It's just organized into layers. Data flows in through the input layer on the left, it gets chewed on and processed in the hidden layer in the middle, and then a final prediction pops out of the output layer on the right. Simple as that. And if we zoom in on one of those little circles, we find the absolute heart of the network. A single neuron. You can think of it like a tiny little decision maker. It takes in a bunch of information, but it doesn't treat it all equally. It gives each piece of info an importance or a weight. Then it adds a bias, which is kind of like a thumb on the scale to nudge the result one way or another. And finally, it passes all of that through an activation function to decide what signal it's going to send out. And here's the thing. Every single neuron in the entire network, no matter what layer it's in, performs these three exact steps, always in this order. First, it calculates that weighted sum of its inputs. Second, it adds the bias. And third, it applies an activation function to generate its final output signal. That's the whole process, right there. All right, so now we have these individual neuron building blocks. Let's see how they're organized into the layers we just talked about. This is really how we go from these simple units to an incredibly powerful network. You see, each layer has a very specific job. The input layer is basically the front door for your data. If your data has, say, 4 features, then you're going to have exactly 4 input neurons. Easy. Now, the hidden layers, that's where the real magic happens. This is where the thinking goes on. They take the raw features and start combining them to create more abstract, higher-level patterns. And finally, the output layer takes all that complicated processing and distills it down into one simple final prediction. Now, inside those hidden layers, the most common activation function you'll see is called ReLU, and it's shockingly simple. If the input number is positive, it just passes it right through. If the number is negative, it just changes it to 0. That's it. This super simple on-off switch is what allows the network to learn incredibly complex, nonlinear patterns, and it's also really fast to compute. But then, when we get to the output layer for a task like, is this email spam or not spam, we need an answer that looks like a probability. For that, we use the sigmoid function. It's brilliant. It takes any number you throw at it, no matter how big or small, and squishes it down neatly into a value somewhere between 0 and 1, perfect for representing a probability. So, how does the network actually know if its predictions are any good? Well, it uses something called a loss function, which is really just a fancy way of saying it has a method for scoring how wrong it is. For a yes or no classification, it uses binary cross-entropy, which really punishes the model if it's both confident and wrong. And for predicting a number, like a house price, it uses mean squared error, which just measures the average gap between the prediction and the real value. All right, that's enough theory for now. Let's see how this all actually works in practice. We're going to build a simple multi-layer perceptron, or MLP, to solve a classic classification problem. So here's the scenario. We want to predict if a student is going to pass or fail their exam based on two simple inputs: how many hours they studied and how many hours they slept. Our little network has two input neurons for those two features, a hidden layer with 3 neurons using ReLU, and one final output neuron using sigmoid to give us that pass-fail probability. And we're going to trace the data for one student who studied for 5 hours and slept for 5 hours. Okay, first our input data, those two fives, hits the hidden layer. Now each of the 3 hidden neurons does its own calculation, weighted sum plus bias. Don't worry too much about the specific numbers here, just focus on the process. So neuron H1 calculates 3.3, H2 gets 4.5, and H3 gets 7.2. Then, each neuron applies its ReLU activation. Since all these numbers are positive, the outputs are just 3.3, 4.5, and 7.2. See? Pretty simple. Now for the next step. Those 3 numbers we just got from the hidden layer, 3.3, 4.5, and 7.2, they become the inputs for the final output neuron. And we do the exact same thing all over again. Calculate a new weighted sum, which this time gives us 5.48. But this time, we apply our final activation function, sigmoid, to turn this raw number into a nice, clean probability. And the result of applying sigmoid to 5.48 is 0.996. So what does that mean? We can interpret this as the model being 99.6% sure that this student is going to pass. And since the actual result for this student was pass, well, that's a very confident and a very correct prediction. So that was classification, a yes-no answer. But what about regression? Let's see how the same basic architecture can work when we're trying to predict a continuous number, not just a class. This time, our goal is to predict a house price based on its size and the number of bedrooms. Now look closely at the architecture. It's almost identical to the last one, but there's one really crucial difference. The output neuron uses a linear activation. All that means is it just outputs the weighted sum directly, without squishing it into a probability. We do this because we want a raw number as our final answer, the actual price. We run the same forward pass calculation again. The data for the house goes through the hidden layer, we get our 3 activation numbers, and those then feed into the final output neuron. The final predicted price it spits out is 151,719 BHD. Now, hold on. The true price was 250,000. So why is our prediction so far off? Well, it's because we started with completely random weights. The network hasn't actually learned anything yet. It's just making its first wild guess. Okay, we have covered a ton of ground. Let's take a moment and boil this all down into a simple cheat sheet with the absolute must-know concepts for any exam. So, if you remember anything, remember this. First, the why. We need neural networks because the real world is messy and nonlinear. Second, the building block, the single neuron and its 3-step dance of weighted sum, bias, and activation. Third, the secret sauce, activation functions like ReLU and sigmoid that let the network learn curves and make sense of the world. And finally, remember that all of this comes together in an MLP, which uses this process called forward propagation to get from your raw data to a final useful prediction. So, we've walked through the entire process of how a neural network takes in data and spits out a prediction. But this leaves one huge, really important question hanging in the air. In our house price example, the prediction was way off. So how does the network use that error to go back and adjust its internal settings to make a better guess next time? Well, that process is called backpropagation, and it's the key to how these networks actually learn anything at all.